Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at our homework for 5.2.5. Our M&Ms here are probability models for multiple events, and it basically just showing you a few different ways that you can organize your list of possible outcomes for these compound events. One way is to create a systematic list, and I don't mind the systematic list so much, but sometimes it can be a little difficult to make sure that you get every single possible combination if you're creating a list, especially if you're creating a list where you're just randomly choosing combinations, you know, like black and red and white and green, and then black and yellow, and then black and red, and then white and red. You know, if you're not doing it in a specific order, this can make things more challenging. So using the probability tables and probability trees are a great way of making sure that you hit every single possible outcome. The thing that's great about the probability tables is that when you put your events, and remember, this really only works when you've got 2 events. If you got more than 2, then you probably want to go with the probability tree. But you create this rectangular array, just like we did for like area models, and you can see every single one of these boxes have to contain some kind of a combination. So just the number of equally sized boxes that you get inside this table tells you the number of outcomes that you're going to have. Now, in this case, you've got 6 total outcomes, right? Because remember, we're trying to look to see, you know, one color here and one color here. So you need to get one of these and one of those. And when we use the word and, we multiply together. So there's going to be a total of 6 combinations. So you may have known going in that your systematic list had to have 6 combinations. But if you don't remember this, then you wouldn't know to look for 6. Whereas if you create a probability table, just seeing that there are 6 open boxes there tells you there's going to be 6 possible outcomes. So you just separate one side. Your 2 outcomes are here, so you break it into 2 equal rows. And here you got the other event with 3 different outcomes. So you got 3 different columns for a total of 6 possible outcomes. With the probability tree, I don't like them going in this direction. I prefer to have your first event, your black and your white here, and then you've got 3 that comes off of that, and you got 3 that comes off of that. I don't know why I like this better. I just do. I feel like you start off small at the top and you can work your way down and spread it out as much as you possibly like. Whereas here, you got to get them spaced properly, and then I found that they start running together. But whatever, you do it whatever way works best for you. But the probability tree is absolutely wonderful for if you have like a 3rd event, like another set of colors, and maybe you have 4 colors in this one, 4 colors for each one of those. So whereas the table is limited to only 2 events, you can have as many events as you want for the probability tree, which makes that very convenient. All right, so what is this about? Marcus and his brother always argue who will be walking the dog. Their father wants to find a random way to decide who will do the job. He invented a game to help them decide. Each boy will have a bag with 3 colored blocks in it. You got yellow, green, and white. Each night before dinner, each boy draws a block out of the bag. If the colors match, Marcus walks the dog. If the 2 colors do not match, his brother would walk the dog. Okay, so Marcus's father wants to be sure that the game is fair. We need to help him decide. So what I'm going to do here is I'm going to just create, let's do a tree, okay? So in the first set, you've got, or actually, or do you want to do it? Now let's do a tree. I like trees. Let me go ahead and thin this marker out a little bit. So the first one, you had your yellow, then you had your green, and then you had your white, right? And then the second one could be a yellow, green, or white. Second one would be yellow, green, or white. Second one would be yellow, green, or white. So we have a total of 9 outcomes, right? Because you had 3 choices the first time, and then the same 3 choices the second time. So that's a total of 9 different outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if the colors match, Marcus walks the dog. So let's see. There the colors match. There the colors match. And there the colors match. If the colors do not match, then his brother walks the dog. So I already see what's going on here. This is not a fair game. So let's take a look. There's my tree right there. It says make a probability tree of all the possible combinations. I should have just read the directions. It told us to do a tree, and whatever. Okay. So yes, we definitely see there's 9 possibilities, and the probability of getting a match was 3 out of the 9, which is 1/3. The definition of whether or not it's a fair game is if it's equally likely, and in this case, it's impossible because you got 9 combinations, right? 9 outcomes. So there's no way you're going to have 4.5 of one and 4.5 of the other. This is not a fair game for them to decide who walks the dog. For Shelly's birthday, ooh, why did I go in that direction? Oh well. For Shelly's birthday, she received 2 new shirts, 3 pairs of shorts. Let me color coordinate. 3 pairs of shorts and 2 pairs of shoes. So I can tell you right now that this event has 2, this event has 3 choices, and this event has 2 choices. So there's going to be a total of 2 times 3 times 2, 12 possible outcomes, and that's what we see right there. So creating the tree, this is what the tree would look like, and you'd see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember, look at the last row or the very end of your diagram to count all the possible outcomes. What are those outcomes? Well, plaid shirt with tan shorts and sandals, or plaid shirt with tan shorts and tennis shoes. Or it could be a plaid shirt with the yellow shorts and sandals, or it could be plaid shirt with yellow shorts and tennis shoes, and so on and so on and so forth. So you can list out all the different combinations. Thank goodness they just asked us to identify the total number of possible outcomes or possible outfit choices, and that answer is 12. And if you remembered our little trick here, you could have figured that out without even setting up the tree. All right, moving on to something else. In 2009, the federal government budget was $3.1 trillion. The government was looking to cut costs. If it decided to cut 1%, how much did they cut? Well, what is 1% of 31 billion? No, of 3.1 trillion? 1%, we would have to set it up this way. We would want to say 3 trillion 100 billion 0 0 0 0 0 0 0 0 0, right? 1 2 3 4 5 6 7 8 9 10 11. Yes, that's it. That is the total, right? And we're trying to find out what is 1% of that. So you can figure that out by using proportional reasoning. And what I would do is I would say, what do you multiply times 100 to give you 3.1 trillion? Well, let's go ahead and do this with the calculator. I needed, I think, 11 zeros, right? 9, 10, 11, yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 3.1 trillion. Then divide it by 100, and you get your answer, 31 billion. So since we're going to multiply that times 1, we don't have to worry about that. The calculator tells us the answer. There is the answer. Now, if the government reduced the budget by 7%, how much did they cut? Okay, so this represents 1%, so 1 times 7 is 7%, so we'll multiply 31 billion times 7, and that gives you $217 billion. So that's the answer here. Then it says, if the government eliminated 93 billion from the budget, what percent did it cut? Okay, well, 31 billion was 1%, which means 62 billion would be 2%, and 93 billion would be 3%. So that's one way of figuring that out. Or you could have set it up like this. You could have said, all right, let's now put the X over here, and let's put our 93 billion 1, 2, 3, 4, 5, 6, 7, 8, 9, and now you use proportional reasoning to solve this. And what I would do is this. I would probably say, okay, let's divide this by 1,000, and I'll divide that by 1,000. divide this by another 1,000, divide this by another 1,000, divide this by another 1,000, divide this by another 1,000. So really, if we just focus on this, 90, oh, what happened? No, why you do that? Sorry, hold on. And we don't need those commas there anymore. Okay, so maybe this makes it easier. So you're going to multiply this times 31 to give you 3,100. So you take 93 divided by 31, and that would give you 3 for an answer. By the way, this is why we invented calculators. You don't have to do all this work paper pencil. Let the calculator help you along the way. All right, integer operations. 7 plus a negative 3. Remember, when you're adding two numbers that have different signs, you're going to subtract. And the reason why, 1, 2, 3, 4, 5, 6, 7, is because you get some zero pairs when the positives and the negatives combine. So 7 plus a negative 3 is the same as 7 minus 3, which is 4. When you're multiplying integers together, there's a different process. And this literally means 10 times negative 5 means we're going to take negative 5 and we're going to repeatedly add that together 10 times. So 10 times 2 is negative 10. I'm sorry, 5 times negative 5 is negative 10. 3 times negative 5 is negative 15. And you keep doing that until eventually you get negative 50. This is the same as problem A, where you got more positives than negatives, so you're going to get some zero pairs there. You end up with 6 minus 5 is 1. And then when you divide numbers, it's the same kind of idea as when you're multiplying. When you divide two numbers that are the same sign, you're always going to get a positive answer. And another way of looking at it is this. When you take any number and divide it by itself, you always get an answer of 1. So the answer has to be 1, positive 1. All right, I feel like we've seen this a little bit lately. Write an expression for the perimeter and the area. Remember, the area is defined by the name of each one of those tiles. So you got 1x squared, 2 x's, and 1, 1. There's your area. Now, as far as your perimeter goes, take a walk around the shape. You know that the x squared tile has sides that are x's. The x tiles has sides that are x's and 1's, and then the unit tile has sides that are 1. So this is the one where you just have to be aware that that would be x, except for this part is not a part of the perimeter. So it's x minus these two. And now you add them together and you get 6x. That negative 2 cancels out with those positive 2, so it ends up being 6x's plus 2. And that finishes our homework. All right, let's move on to the next activity. Take care. Bye.
Hey, feeling good, like I should.